Entebbe. Somero ly'abawala n'abalenzi lusomesa arts ne sciences okuviira ddala ku siniya esooka okutuuka ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory, ssaako ne computer lab wamu ne bw'osomeseza omwana wo mu masomero ga Giant Schools omuli kampasi y'Ebombo Kalule n'ey'Ekabalagala toba na bweraliikirivu bwonna olw'omusingi okutambuzibwa ebyenjigiriza n'ensoma y'abayizi ey'omulembe. Mu masomero gaffe gano gonna tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuuka ku siniya ey'omukaaga nga tusomesa abaana okuviira ddala ku mutendero gwa kindergarten okutuuka ku kibiina eky'omusanvu. Tulina abasomesa abakugu mu kubangula abaana n'okubateekateeka. Ebibiina abaana mwe basomera eby'omulembe omuli buli kimu ekikwata ku ebyo bye basoma, ebisuula ebyazimbibwa obulungi, ebigazi ate nga biyonjo. Okumanya ebisingawo tukubire ku nnamba z'essimu ez'owammanga.
Weewaawo abalabi baffe mwenna mbalamusizzaako nnyo, mujebaleko gyonna gyonna gye mutuusizzaako engalo. Akadde keeko ng'enteekateeka weebadde nga erangibwa nti kati essaawa zaakyuseemu. Essomo ery'abayizi aba siniya ey'okuna kw'ogatta n'abookusatu kati liri ku ssaawa 9 mpaka ssaawa 10, so ate bannaffe aba primary bo bazze ku ssaawa 4 mpaka ssaawa 5. Mu buufu obwo njagala okutwala omukisa guno eno okwongera okuba omulange eri abazadde mwenna n'abayizi baffe mwenna abayinza okuba nga mutulaba ku ssaawa eno nti mugezeeko okutegeeza bannammwe nti empeereza ate yakyuseemuko wano okuva mu studio. Abayizi aba siniya ey'omukaaga tetubasuuliridde, wabula ate mmwe tugenda kuba nga tubeeranga nammwe butereevu mu ddiiro lyo buli lwa mukaaga okuviira ddala ku ssaawa 12 mpaka ssaawa 2 ez'okumakya nga tulina essomo ery'okubala oba physics paper 2 n'essomo lya chemistry, ate olumala tubeeyongeze mu budde buli obwa ssaawa 6 mpaka ssaawa 7 nga tusoma essomo lyaffe erya economics oba ery'ebyenfuna. Ku ssaawa 7 mpaka 8 njagala okubajjukiza nti tujja kubangayo n'essomo erya physics paper 1 then n'essomo erya biology lijja kuba nga libeerawo okuva ku ssaawa 9 mpaka ssaawa 10. N'olw'ensonga eyo tusaba bambi mugezeeko okutegeeza bonna bonna bekikwatibwako nti empeereza yakyuseemuko, naye era mwekuumire ku TV ya Ssaabasajja BBS Telefina obulango obwo bubajjukiza mujja kuba nga mubulaba. Saagala mbalwiseeyo. I would like to welcome you, my dear viewers and candidates of the Senior 4 class, to today's show. Previously, we have been discussing Achimedi's principle. This is what we last talked about on our previous meeting, where I talked about the story of the famous wise man, Archimedes, from which the principle is derived. And I also gave you an insight of how he came about to discover this theory relating the upthrust force to the weight of the liquid displaced or the fluid displaced. So I went on and I also tried to go through the procedures that we follow in our traditional lab setting as far as verifying the principle is concerned. Today I'm here to share with you some little bit of calculations, or what we call the numerical form of the questions that are requiring the application of the principle. However, I must also note that at the end of today, be assured we'll leave an assignment and more of these questions to do with the Archimedes principle on our school kit app. Whoever has not yet downloaded it, please remind your friends that they shouldn't miss out, especially with the change in the programs. We are trying to see that we bring you the best during this lockdown. So the school kit app is also available for download on the Google Play Store. Don't forget to download it. And then it is on that application that you're going to find the different forums that the different teachers from here at BBS Somera Muddiirolyo have opened up to try and ensure that we extend the learning. It goes beyond the 45 minutes, 1 hour that we have on air. So with me is my first example, which is talking of a metal that weighs 20 newtons in air and 15 newtons when fully immersed in water. And then they're asking us to calculate the upthrust force that this metal will experience. So, because I know my weight in air, it is my habit to always summarize numerical problems because it eases the job of trying to work them out. And then this is the weight in water, which I'm going to call WL. This one is 15 newtons. So I'm going to use my definition of upthrust being the apparent change in weight of an object which has been immersed in a fluid. And of course, from our previous lesson, I mentioned that the apparent loss in weight is the weight in air minus the new weight when the object is wholly or partially immersed in the fluid. So in my example here, I want to mention that by definition, upthrust is apparent loss in weight of the object and this is the weight in air minus the weight in the liquid, which will be 20 minus 15, giving me 5 newtons. This is an example of a numerical problem which you may come across paper 1, the objective section, section A, at the ordinary level, where we can quickly give you the weight of a substance in air and then also we give you its weight when wholly or partially immersed in a liquid, and then we require you to determine the upthrust. So using this definition, we can be able to deduce the upthrust that this body will experience, or the apparent loss in weight that the body will experience when wholly immersed in water. Now they're asking us to calculate the volume of the water displaced. Remember, we said that last week the upthrust has got two definitions, or it has two meanings. During the verification process, we also discovered that this apparent loss in weight is equivalent to the weight of the liquid displaced as a result of lowering this metal into water. So when they're asking me to calculate the volume of the water displaced, first of all, I must recall that from the definition of upthrust, this will be the weight of the water displaced. And if this is the weight of the water displaced, then I can use the definition of weight being mass times acceleration due to gravity, and then I'm going to substitute for mass being the density times the volume, from which I'll be in position to determine the volume of the water displaced. This is what I'm saying. We recall that upthrust is also equal to the weight of the water displaced. So what does this mean? It means that these 5 newtons are equal to the mass of water displaced multiplied with acceleration due to gravity g from the definition of weight. So it means that 5 will be mass is density of the water times volume of the water and then times g. So from this, I have that 5 will be density of water, which is known to be 1,000, multiplied with acceleration due to gravity, which we can take to be 10 at this level, and then multiplied with the volume of the water that will be displaced that we're looking for. So the volume of the water displaced will now become 5 divided by 10,000, which will lead to 5 exponent minus 4 meters cubed. Why? Because I substituted for my density when it is in kilograms per meter cubed, and therefore the volume must correlate with that unit of density that I've used. Now, what I've just done here is exactly what happened during the ancient times when Achimedi was trying to solve the task that was presented to him by the king in trying to discover if his gold was cheated or it was stolen by the smith who had assigned the duty of making a crown out of it. I remember telling you and indeed sharing with you the story using the animated video that we got from YouTube, whereby if we knew the density of something, and then we also happen to know the volume of the water that it can displace, then it means that indeed we can be in position to determine its weight. So this is now the reverse. I know the weight, but I'm looking for the volume given the fact that I know the density. So Achimedi worked using the same principle, only that the story is the reverse of the mathematical problem that we're being presented with today. So this will be the volume of the water displaced. Moving on, they're also asking us to determine the density of the metal. Now, how are we going to determine the density of the metal? Remember that this metal was whole or fully, as they have used in the question. It was fully immersed in the water. Now, this is what happens. When we immerse, I hope that all of us remember the method for determining the volume of an irregular object using the overflow can during our senior 1 lessons, where we refer to lowering the object into the overflow can and then measuring the volume of the water that spills out. And then we make a deduction that the volume of the water that spilled out is equivalent to the volume of this irregular object. So it's the same knowledge that I'm going to use here. Why? By definition, if you remember from the primary science, volume is the space occupied by an object, which means that when I lower an object into this can, such that I have some water spilling out, then it means that the water is only spilling out, reason being the space which it was supposed to be occupying, or the space which it preoccupied when this was not yet lowered into the can, is now being occupied by this metal or by this object. I'm trying to use the layman's understanding of the term volume in relation to the mathematical problem that we are faced with. Why? Because I want to make a conclusion that if this is the volume of the water displaced, then it corresponds to the volume of the metal. Therefore, using the definition of density as mass over volume, I can be in position to determine the density of the metal. After all, I know its weight in air, because from its weight in air, I can be in position to know its mass. I hope that I'm not rushing through this. Why? Because I've chosen to do question 1 and help me answer like 3 common questions, which I usually set, of course, because of the time that we have in order for us to have this discussion. I'm first of all introducing to you the question on upthrust, given weight in air, and then also given weight in a liquid. Then I'm also introducing to you the question of finding the volume of the water displaced, or the volume of the object that was immersed in the liquid. Reason being, from my definition and the explanation which I've tried to give you in relation to that experiment which we carry out practically in the lab, because we do this practically in the lab in Form 1, when we are trying to study about discovering the different volumes of, the volumes of different objects. That is what we do. And then we come to a conclusion that the volume of the water that spilled out is equal to the volume of the object that was fully immersed into the overflow can. Why? The definition of volume is clear: space occupied by an object. So the metal is coming in to occupy the space of the other water which has flown out. Then number 3, I'm also introducing to you the question of determining the density of the metal. It is because from this, I'm then going to introduce to you the first application of Achimedi's principle in determining the relative density of a metal or of a solid object. So this is my solution to Roman 2. This is my solution to Roman 1. I'm trying as much as possible to be very audible and then also very inclusive in my calculation because I chose this topic. Very many people were suggesting it to me in my email, an indicator that probably many people were finding challenges. And I would like to share with you the easiest way of going about this topic because it's quite an interesting topic. It's very practical given what we have shared so far. It has interesting stories and backgrounds to it. So, Roman 3, I'm going to establish the density of the metal. So, by definition, I'm saying that density is mass divided by volume. But since the weight in air is known to be 20 newtons, we know that this is also mass times acceleration due to gravity. So the mass of my metal or my solid is going to become 20 divided by 10, which will give me 2 kilograms. Now I know the mass. Then the volume, this one I've said it will be equal to the volume of the water displaced. Why? Because of this background that I've just shared with you. The background which we learn from primary science and indeed also senior 1 physics. So, I'm going to put a however from the theories of volume, comma, the volume of the water displaced is equivalent to the volume of the metal. Why? Because we said if this is coming in so that water spills out, then it means that what is spilling out is being replaced by what is coming in. And it must be of equal magnitude. Again, experiments prove this. We do this in the senior 1 physics. So the volume of the metal, I'm going to abbreviate it as VOL. Kindly work with me. Volume of the metal will now become 5 exponent minus 4 meters cubed. Hence, the density of the metal becomes the mass, which is 2 kilograms, divided by the volume, which is 5 exponent minus 4, giving me 20,000 divided by 5, I think around 400 or 4,000. Density, 1,000, yeah, 10,000, yeah. I think this is 4,000 kilograms per meter cubed. Just to verify it, let me go through it with my calculator here. You can also go through it. Yes. So, indeed, it's 4,000 kilograms per meter cubed. Oh, I had written 400. Yeah. So this is the density of the metal. Now, I'm going to move on and do another calculation. But in my next calculation, I'm going to try and spice things up. This is what I have. I hope that people are through with writing this. Let me give my question 2 here. Now, my question 2 reads that an iron cube of volume (800 cubic centimeters) is totally immersed in A, water, and B, oil of density 0.8 grams per centimeter cubed. Full stop. Now, the question is calculate the upthrust in each case. Calculate the upthrust in each case. Now, all of these are questions which you've probably been coming across in the different past papers, and maybe some of you have found it difficult in trying to attempt them. So today we are here to try and find ways of dissecting them in order for you to not be scared anymore when you come across such a number. So this is what we have. I have an iron cube of given volume, totally immersed in water, and then again totally immersed in oil of density that. Now they asked me to calculate the upthrust in each case. Number one, the question is clearly communicating that the upthrust experienced when this cube is lowered in water will be different from the upthrust experienced if it is lowered in oil. So for us, we're going to understand two things. First of all, we're going to answer the question. And then number two, we're going to also get to know what determines upthrust. But it's very clear that the changes in upthrust are most likely to arise as a result of the changes in density. Why? Because this is density 0.8, of which we know that water is density 1,000 kilograms per meter cubed, which is also 1 gram per centimeter cubed. So, upthrust is a force which must be stated in newtons. Now, I'm also bringing to your attention a question which may require you to calculate the upthrust experienced by an object when immersed in a fluid, but then they have not given you its weight in air, and neither have they given you its weight in the fluid. But what they have given you is simply its volume, and they have mentioned that it is totally immersed. So here, we are going to use the definition of upthrust as weight of the liquid displaced, but rather not the apparent loss in weight, because we do not have information about its weight in air or its weight when immersed in the liquid. So using the definition that upthrust is weight of water displaced, of course for case 1, I'm going to have the weight of the water displaced being number 1, weight is mass times acceleration due to gravity. This is mg. But we saw that m is also density times volume, then times g. So the density of the water is known. The volume of the water displaced, according to our previous calculation, will be equal to the volume of the cube. In fact, let me put it here as a note that the volume of water displaced will be equivalent to the volume of the cube, which is given as 800 centimeters cubed. So my upthrust is now going to become 1. I'm using density in terms of grams per centimeter cubed. Why? Because I have a volume which is in centimeters cubed. Now, I do not want to go through the process of converting this into meters cubed so that I can use the density of water as 1,000, which is common to us, and then later on multiply with G. That will be, students usually find it difficult to make this conversion from centimeters cubed to meters cubed. Now I want to do this in the simplest manner. How? When I use the density in grams per centimeter cubed, let me include the units. I'm only including the units for purposes of ensuring that people understand what I'm doing. But it's not necessary when you're making your presentation to include the units. Multiplied with the volume, which is 800 centimeter cubed, and then with acceleration due to gravity, which is 10 meters per second squared. Now, when you look at this, we may arrive at a unit which is not the SI unit of earth thrust force. Why? Because multiplying this alone, this will cancel out, then I'll remain with the mass in grams. So the mass in grams cannot multiply the acceleration in meters per second squared in order to give me the derived unit of a Newton, according to the knowledge of dimensions. So what I'm going to do, after discovering that this multiplied with this leaves me with the mass in grams, how do I convert from grams to kilograms? Now this is usually easier. When you're making the conversion from grams to kilograms, we know that 1 kilogram is equal to 1,000 grams. Therefore 1 gram is 1 out of 1,000 kilograms. So I'm going to divide this. By 1,000. Yeah, because this will be 800 grams. Yeah, converting it to kilograms, I divide by 1,000. Now, when I divide by 1,000, this will bring me to the value of 800 times 10 divided by 1,000. But now, this matches the unit that I'm looking for, which is a Newton. So here, I'm going to go on and then deduce the upthrust force experienced as 8 newtons. This for the case when the object is in water. The upthrust force that it will experience will be 8 newtons. Alternatively, let me talk about the alternative. For those people who are already familiar with the conversion of cubic centimeters to cubic meters. Remember, 1 meter is equal to 100 centimeters, which means that 1 centimeter is 1 out of 100 meters. So if I'm now to cube that, it means that 1 cubic centimeter will be equal to 1 over 100 cubed meters cubed. I don't want to go back on the lesson of metric system, but alternatively, somebody would have said that the upthrust U is also this in 1,000, of course stating the unit of kilograms per meter cubed, and then multiplied with this in meters cubed, which will be 800 times 1 out of 100 brackets cubed, and then multiplied with 10. Definitely this is true, because this will be 800 times 10 power minus 6, and then the minus 6, the 3 will take away part of it, and then also this 3 will take away the remaining, leaving us still with the upthrust as 8 newtons. I really hope that my viewers out there are following me in trying to emphasize on the conversion. Either you can do this or this. The choice is yours. However, the physics already ended at this point, where we are applying the fact that upthrust is weight of water displaced, of which the weight of water displaced is the mass times acceleration due to gravity, and mass is density times volume. So the remaining part is yours, playing around with those conversions. But you can either do this or that. Now, in fact, let me do the one of oil using the alternative method that I've just given you here. Part B, when immersed in oil, upthrust will be equal to the weight of the oil displaced. And of course, the weight of the oil displaced will be its density times the volume, then times G. But we've already said that the volume of oil displaced will be equal to the volume of the cube, which is 800 centimeters cubed. And this one is the same as 800 times 10 power minus 6 meters cubed, if you're to do the conversion, this part here. So it means that the upthrust in oil is now going to become the density of oil, density of oil is 0.8 grams per centimeters cubed. Now, this is very easy. How? Water is a standard which helps us remember this unit very fast. According to this, you're seeing that 1 gram per centimeter cubed is equal to 1,000 kilograms per meter cubed. Therefore, when I'm converting from grams per centimeter cubed to kilograms per meter cubed, I'm just simply multiplying with 1,000. And this will bring me to 800 kilograms per meter cubed, because I'm just multiplying this with 1,000. So the upthrust in oil will now become 800 multiplied with 800 exponent minus 6, but we could also further break this down and write it as 8 exponent minus 4, but let me take it like that, and then multiplied with 10. So this is 1, 2, 3, 4, 5. And then 8 times 8, that is 64. That is 64 exponent minus 1, I think we get something like 6.4 newtons. Let me just confirm it. Yeah. So this is the upthrust experienced when in oil. Now, where is the upthrust bigger? Or where do you experience more loss in weight? Or where are we going to experience, where are we going to find it easier? Where are we going to find it easier to lift a jerry can or an object when immersed either in water or in oil of this density? I'm trying to think of all the practical events that can happen around us in order to relate with this question. Because remember, I told you that the effects of this we experience every day, whereby if you try to lift something when it is immersed in a liquid, you're going to feel that it's a bit lighter. It's not that heavy. It's not having its normal weight. It will be much easier for you to lift it when it is immersed in this liquid. Now we are wondering, where will it be much easier? Is it when the object is immersed in water or when it is immersed in oil? And the values of the upthrust that we've just got answer that question. Why? We are seeing that here we are going to experience a change in weight by 8 newtons, a loss of 8 newtons. Yet here we're going to experience a loss in weight of only 6.4 newtons. So it is true that since here we're experiencing more upthrust, we are being supported more by the liquid because it is causing a change in weight of 8 newtons. It is where we are going to find it much easier to carry the object while immersed in that liquid, water in this case, compared to this. Of course, even here we are going to experience a change in weight, but it will not be as much as if it were in water. Now, what affects this? It is simply just the density. Because here it was 0.8, and then the other side it was 1 gram, or 800 kilograms per meter cubed vis-a-vis the 1,000 kilograms per meter cubed of water. Now, those are other questions which can arise from this. Remember, in the objectives of paper 1, that is section A for the senior 4 students, there are always those questions. There are some which are numerical, then the others are theoretical. But again, there are some theoretical questions which we can derive from the numerical situations, just like what I've talked about. The examiner can present you with a question of giving him information on where it will be much easier to lift an object when it is lowered into two liquids, and then they mention the density of the liquids. One may be of 1,000 kilograms per meter cubed, and then the other one of 800 kilograms per meter cubed, stating reasons why. I hope that people are following me on that. Or they may present you with funny alternatives, but then you have to use the knowledge that we have just shared today in order for you to answer that correctly. So this is my second example, and I hope that people out there are enjoying and learning something with me. However, allow me now look at my last example, which is the last form of the question that we can expect during our exams. So this one reads that, this is going to be my question 3, I guess. An iron cube of mass 480 grams and density (8 grams per centimeter cubed) is suspended by a string so that it is half immersed in oil of density 0.9 grams per centimeter cubed. First off, find the tension in the string. Now, if there are any senior 5, senior 6 students who are following us, then you must note that these calculations, the way we are doing them with the O-level students, can also be presented to you in paper 1, section A at any time, because the Achimedi's principle doesn't really change that much, minus the few other details that we see at the advanced level. So I'm kindly calling upon you to take this opportunity and do general revision with us. Those of you who have already done the topic, and maybe the senior 5s, they can even take these notes because they will also be beneficial to them at a certain point. So this is what we have. Have been given an iron cube of certain mass and density, suspended by a string so that it is half immersed in oil of that density. Then they're asking me to find the tension in the string. Yes, they're asking us to find the tension in the string. Now, I want to model this using such a diagram. So I have my object. I hope people can see the colors. I'm going to try and use some colored chalk, assuming initially the water level was here. Then, on introducing this cube, the water will rise so that it reaches halfway. Now, what do we know? Number 1, there is an upthrust force. Number 2, there is also a tension force but at the same time, there is a weight of the object. And this will be apparently its weight in air. So we have those three forces. We have those three forces acting. One is the upthrust, and then the other one is the tension, and then we also have the weight of the object. So at equilibrium, we can agree that the forces acting on the body upwards must be equal to the forces acting on it downwards. And in this case, it is the tension in the string plus the upthrust, which must be equal to its weight that it is exerting within the liquid. So, what I'm going to first of all do is determine the weight of the object, because I know its mass and I know its density. Number two, I'm going to establish the upthrust. And the upthrust must correspond to a certain volume of oil displaced, which accounts for only half of this being below the water surface. Below the oil surface. We are dealing with oil. So, after doing that, I think I'll be in position now to determine the tension in the string. So we're saying that at equilibrium, T plus U is equal to W. T is the tension in the string. U is the upthrust in the oil. W is the weight of the cube. So, what is W? It is mg. And this will be 480 divided by 1,000 when I'm trying to convert it to kilograms, and then multiplied with 10. So, 48, so this will be like 4.8 newtons. Step 2, what is the upthrust? U. U is equal to the weight, by definition, of oil displaced. And the weight of the oil displaced will be the density of oil times the volume of oil displaced multiplied with G. But the volume of oil displaced it is equal to a half of the volume of the cube. Why? The question mentioned to us that an iron cube of this mass and this density is suspended by a string so that it is half immersed in the oil. So, the volume that is being displaced is only ensuring that half of the cube is being immersed in the oil. So that's why I'm taking it to be half of the volume of the cube. And I really hope that my viewers and my learners out there are following me through this calculation. Because this now seems to be one of the tricky ones. But again, it's not so tricky for as long as you understand the theories of Archimedes. Remember, we are revising over 3 topics here. Archimedes' principle of its own, but then the topic of measurements. Why? Because we are playing with conversions. Number 3, we are revising the topic of volume itself. Those are senior 1 topics. Maybe also the Archimedes principle, which I'm introducing now. So, this is just from the definition of volume, space occupied by an object. Now, this volume is going to be a half times, I don't know the volume. I don't know the volume of the cube. So, let me first find the volume of the cube. Input, however, that the volume of the cube from density being mass over volume, volume is mass divided by density. I hope people get me well on that. Mass over density. So this is going to become mass of 480 divided by density of 8. What do we get? 480 divided by 8, we're getting 60. So the volume of the cube is 60 cubic centimeters. Why? Because this was in grams, and then also this was given in grams per centimeter cubed. So that is the volume of the cube. Now, what is the volume of the oil displaced? Hence, volume of oil displaced is a half times 60, which will give me now 30 centimeters cubed. This is very important here. I hope that. This is the volume of the oil displaced, which is half the volume of the cube. But even the volume of the cube was not given directly. So the volume of the cube, I've used the definition of density being mass over volume, then I've made volume the subject. Remember this. So volume is mass over density. If you make V the subject, this is what I've played with to come to this point. So now that I know the volume of the oil displaced, it means I can go on and find the upthrust, because my interest is in determining the upthrust, which is density of oil that I was given multiplied with the volume of oil displaced that I've just found times acceleration due to gravity. So, volume, upthrust will now become density of oil, which is 0.9, multiplied with volume, which is 30. But then I told you I'm going to divide by 1,000, because 0.9 times 30 is representing a mass in grams. So I have to divide by 1,000 to convert it to kilograms before I then multiply on the acceleration due to gravity. So this goes, that goes. I remain with 0.9 divided by 100. I'm getting a very, very small upthrust, which is 0.009. Let me just press my calculator again to be sure. I have 0.9, which will also be times 30. 0.9 times 30 multiplied with 10, that is 270, then divide by 1,000. It is taking me to 0.27. Yeah, 0.27 newtons. Now, what is the tension? Of course, now I can find the tension. So, using equation star, I can deduce that the tension is the weight minus the upthrust, which is 4.8 minus 0.27, giving me 4.8 minus 0.27. This gives me 0.53 newtons. Sorry, 4.53 newtons. So, that is another form of the calculation which I would like to end with today. And because of time, I've promised that I'm going to leave an assignment, and indeed the notes that I've used during the Achimedi's principle on the school kit app under my forum. Otherwise, I would like to thank you for being very good viewers, and kindly note the changes in our airing times so that you can always keep following us. It's been a blessed day for me, and may the good Lord bless you all. I sign out.
Somera Muddiirolyo ng'ewagiddwa Maryland High School erisangibwa Entebbe, ssomero ly'abawala n'abalenzi